Hi, Mark here with My Engineering. In this video, I'm going to explore how to achieve the highest level of accuracy using a blue light laser scanner. So, for context, for this particular video, we're going to be focusing on local accuracy. So I'm going to be using a small to medium range scanner, in this case the Scanology SimScan 42, and I'm going to be using a small object. So this is going to largely ignore volumetric accuracy. We're going to get into that in a different video. What I'm going to be focusing on is how to use the scanner to best achieve the highest level of local accuracy. These tips and tricks can be used in your everyday workflow no matter what you're scanning and what your end purpose is. But where it's really going to be critical is when you're actually in the metrology range of scanning. So this is a metrology grade scanner. It is accurate to about 0.02 of a millimeter, so that's about 0.8 of a thou. When you're scanning tolerances for, say, QA and QC are going to be in the thousandths of an inch kind of range, it's critical that you actually use this properly to get the maximum results that you intend to achieve. Now, the first one I'm going to talk about is normalizing the temperature of the unit itself. So not only is it affected a lot if it was stored in a cool environment. Right now, it's minus 28 Celsius outside, really cold. If this was sitting in my truck and I brought it in and started scanning, other than the fact that the lenses are going to fog over right away, everything is going to be changing shape as it warms up. Same thing if it was sitting in the cabinet at 20 degrees and you go out and you start scanning with it. After about an hour of this thing being plugged in, it's warm to the touch. It's not hot, but it's warm. And so what that means is all the internals on this thing, so the sensors, the lenses, the projectors, everything is just ever so slightly changing shape. So you want to get it to its normal operating temperature, and it's going to kind of sit there and level off. And that is when you want to get into our next stage, which is calibrations. And I cannot stress how important it is on the daily, especially with lower grade scanners, to do more than you think is necessary of the field calibrations. So if it really matters to have a good tolerance, a good accuracy with your scanner, with whatever operation you're doing this at the start of every day, at the start of the scanning, but also if you're scanning throughout the day and so let's say the temperature in the shop environment is changing, or there's maybe the scanner is getting really hot because you've been using it a lot, it would be beneficial to redo the calibration process in order to make sure that you're at that highest level of accuracy the scanner can achieve. For the amount of time that it takes, and this is something that's very easy to ignore, it should only take 15 to 20 seconds once you're comfortable with the scanner and if you've done the process a lot. It is going to benefit you down the road doing it more often than you think is necessary. I would recommend for a lot of users, if you are in the QA, QC kind of environment, do one at the start of the day, do one again after coffee, do one again after lunch. It's not going to hurt, it's not going to add any extra time to your day, and it is going to give you that confidence and reliability in the data that you're actually collecting. So the next one we want to look at is your scanning range. And you can see on the left-hand side of the viewing window, there's that little indicator bar for indicating our distance. And right now I'm at the very extreme end, so that little blue indicator, very end of the bar. So I'm still collecting data, but I'm at the farthest range for where these lenses are triangulating to get good data. It is good for getting large areas quickly, and there's definitely a use case for scanning in this mode, but when accuracy matters, the lenses are tuned to be at a certain range to get the most accurate data. And where that actually is closer to like the 40% range. So if you picture at the middle there, it's about 50%. Go a little bit closer there. That's where you're going to get the most accurate data for these lenses. Now you can go in quite a bit closer, and so you can see that indicator is starting to turn red. We're at the near end. And that would be useful if you need to get really good fine geometry, but your accuracy overall tends to drop off. It gets a little bit noisy because you're pushing the limits of where those lenses are getting good data. So that 30–40% range, that's the sweet spot for almost any scanner, and that's going to give you the best results. The next one we're going to talk about is markers, these nice little reflective targets that we stick all over all of our pieces. Essentially, the scanner requires at least 4 of these little targets in the field of view at all times. Some scanners will let you go down to 3. Definitely don't recommend that because it is one less angle that is triangulating to try and fine tune where that little laser point is going to be registered. You want to have at least 4, but there isn't a limit. So here on this piece, I only had a few markers. There wasn't really quite enough on here to do a proper scan. At certain angles, like there, you can only see 2. Put it on something like this turntable here, where I just have it plastered in markers. As long as the piece itself is stationary relative to where all the markers are laid, it's going to register just fine. So the good example is all of my workbenches in the shop here are just covered in markers. Lots of them and random. That brings me to the next little thing, random. You see on the sheets that these markers come on, they are completely uniform in both directions. Terrible for the scanner. So this looks the same as, this or whatever. You want them to be as weird, random, and oriented in different planes as possible. Having them just on a turntable like this, you have a nice XY kind of field going on. You don't have any Z, so any depth to it. Change the depth, change the angle, change the randomness, and don't worry about having too many. That said, applying and removing targets is a little bit tedious, and you're likely over time to try and do it less. You want to find ways to make it easier. Here we have these magnetic little 6mm targets available on our online store. You just pop them on, take them off, and reuse them. You're not using a lot of stickers, and they come off a lot easier than stickers. We also have these magnetic marker blocks, so they can be seen from multiple angles. Very nice, handy for covering large areas very quickly. Then you can get a little bit creative and start making your own. So we made these 12mm target marker blocks. So for larger objects, when you're using the longer range scanning modes, also magnetic, super handy. You start to get very custom. So we have these flange paddles that one of our engineers made with magnets on the back. Do what works best for you. Find solutions that will make it easier for you to do the work so that you're more likely to do it well. Again, stickers, super necessary, very important. Or I should say targets, very important. You don't want to make it a chore to put them on and off because then you're going to do less of it. Next critical piece is not only having enough markers, but properly scanning them in. So when you're doing your marker scan before you're doing the actual laser scan, and I will acknowledge some scanners you can do both at the same time, so simultaneous collecting the markers and laser points. I don't recommend that because it's not as accurate in terms of registering where those markers are in space. It's wherever it was first seen, that's where it places it. It's not good enough when you need accuracy. So when you're first doing your marker scan only, make sure that you scan your markers from multiple locations. In the Scanology software, so DefineSight, it'll register when you're looking on your screen. You'll see the little marker as soon as the scanner registers its location. It's going to be measuring that off of all the other markers that it can see at any given time. But you want to make sure that you capture that marker from multiple different angles. In the DefineSight software, when the scanner can see the target, it is green. As soon as you move away from it, it'll either be white or blue. So blue, it knows where that target is, but it's not fully registered. You want to capture it from a lot of different locations for it to turn white, and then you know that's a fully registered target. And so everything that is measured off of that target is going to have a very accurate location. One little item I'm going to touch on ever so briefly is some scanners have the ability to track on geometry rather than using markers. That can be very handy in some cases. It could speed up your process, a little bit less prep time. But the problem with that is geometry tracking is just not accurate enough. It will probably produce a good looking model, but it is not something that you can measure off of. I would not call that metrology grade. Markers are critical. The next one is surface preparation. So this is one that most people tend to overlook, and I myself am guilty of it. If I try and scan a surface and it scans reasonably well, I'm not too worried about it. But when it comes to accuracy, you need to have a very good solid return. For demonstrations, I like to use this coffee cup because it has all of the worst surfaces to scan on it. Matte black, it absorbs light, so you're not going to get a good return. Other surfaces that are really bad is like black rubber, maybe carbon fiber. It just doesn't reflect light very well, so the scanner doesn't have a very good return to actually register that point in space. The next one is very shiny surfaces. So stainless steel, usually not as bad as you think it would be because it is even though it is kind of mirrored, it does tend to reflect reasonably well. Sometimes you'll get a little bit of 3D noise on that surface though. This is more like a brushed aluminum on here. It is actually quite tough. If you just try and scan it straight on, you might get a little bit of data, but on the most part, it's going to look like there's nothing there. The last one is transparent. So light passes through something like glass or acrylic or plastic, whatever this might be. It's just not going to have anything bouncing back for the scanner to record. Very simple. Scanning spray. We like to use this Adablime, the sublimating spray. My favorite one is the AB6. It totally evaporates off in about 6 hours, so you don't have to worry about washing the part afterwards. Black object like this will not scan very well. You just give it a light dusting, and it kind of turns this nice little white powdery finish to it. That's enough for the scanner to work on. You don't want to overspray, you don't want to add thickness. So again, if we're working in the metrology range, you don't want to add thickness to the part itself. Just a little bit of a dusting gives it a reflective finish that the scanner will bounce off of and give you the results that you're looking for. Before we move on from surface preparation, I want to make sure that we spend a little bit of time on surface cleaning. And this is very, very important, especially if you're in manufacturing where you have things like cutting fluid or greases or something on that surface. Water is also another one. Scanning spray will be completely ineffective if there's some of that on the surface. It'll just basically disappear. Also, things like water, grease, any dust or cuttings that you might have on there is going to add thickness to that surface. So if you have to have a clean surface, it's critical that you take that kind of stuff off. Another one that we see, and this is more on the, we see this a lot in our leak sealing department, where you have a surface that was previously insulated, like a pipe. And then you remove that insulation, you got to scan this pipe. There's a little bit of that fuzz left over from that mineral wool or rock wool. And when you're scanning, it'll actually add a little bit of 3D points in space, so that point cloud has a little bit of noise on it, because there's actually physically something there. So if you need to have a clean scan, it's imperative that you have a clean surface first. Something else we could do to try to minimize the amount of error while scanning is move the scanner as little as possible. So something that might be very useful is using a turntable like this. This is just a cheap turntable. Put the part on there and rotate it around while not moving the scanner. Or if you can even put the scanner on a tripod or maybe even in a cobot arm. But what you want to do is not have the scanner moving around too much. I'm going to relate this a little bit back to photography, where if you have a long exposure and you move the camera, you get a little bit of motion blur. Something similar can happen with the scanner because it is taking a bunch of different exposures. And so if there's a little bit of movement in that exposure, there's going to be a little bit of movement in the scan data as well. They're very short exposures when we're talking about laser scanning, but it is an exposure all the same. So you don't want to have any motion in the scan data itself, because it would just kind of come in as 3D noise. Also, some scanners are equipped with IMUs, and so the more movement that you have with the scanner, if you're going a little bit crazy, that's fine if you're on low accuracy tolerance. So if I'm scanning something very crude where it's not going to matter at all, I can just move the scanner like this. It's collecting data fast enough. It will get all that you need. But when accuracy is very important, actually keeping the scanner still during the scanning process will improve your results. The next one we're going to talk about is triangulation. So the way that this type of scanner works is you have the projector here in the center. It's projecting laser lines on the object, and this sensor are both looking at that object and triangulating where that point is in space. And so when you're looking at an object like this, you want to be able to move and change the angle at which it's hitting that object in order to triangulate it better. Because not only are you triangulating between the projector and the two sensors, you're also kind of triangulating between the known points, which are these little reflectors, these targets, if you will. So if you hit a target and you're triangulating from this angle, and then you do it again from this angle, it's just going to give you a much more reliable data where that point is in 3D space, because again, we're always working in 3 different axes. The last topic that I'm going to cover in this video is going to be post-processing. So this is where we take our raw data and transform it into an STL or an OBJ, something that we can use in the next piece of software. We don't want the post-processing algorithm to actually change the data. So there's a few different things that it's going to give you as options. One might be fill the marker holes. All that's going to do is going to take the data from around where that marker was and extrapolate that to kind of fill it in. If you're using that surface to measure, let's say if it's a plane, you wanted to do flatness, it's going to just take the edges of around where that marker was and fill it in. It might be very close to what that piece actually was, but we don't know, and so we don't want to invent data that is going to give us some kind of a result that may not be actually accurate. The next ones are smoothing, boundary sharpening, and all that's going to do is change the data to make it a little bit nicer. Now, smoothing is kind of a tricky one because if you have a very tricky surface that you're trying to scan, it might have a little bit of 3D noise to it. Smoothing will actually flatten it out, smooth it. What it is doing though is it's taking the data that was there and just changing it to what it thinks it should be a little bit more correct. And it may actually be worse than what is actually there. If the surface actually did have noise to it, if it's a little bit rough, it will actually flatten that out and make it look like it's smooth, and that's not actually what's going on. The last one is going to be hole filling. It looks much nicer when you have a watertight model, or at least not very many holes in it. But all that the software is going to be doing is taking data from around where that hole is, where it doesn't have any data, and just pulling it in, extrapolating, inventing data, if you will. It'll look a lot nicer, but it is not realistically representing what was actually there. It might, again, be incredibly close, but if you're filling holes, it's not the original data. It's just new data that the software is inventing. The last one I'm going to touch on is splicing. So if we had to scan this object twice and then flip it over, if you scan it once, flip it over, and want to tie the two models together, laser point splicing is not as accurate as marker splicing. All you're doing is picking common features and then fitting it together loosely, and it'll do a best fit. Best fits are generally pretty good, but they can be out by several thousandths of an inch. Marker splicing is generally as close to perfect as you're going to get. Most often, as long as the markers don't move relative to each other, so if you had magnets and you accidentally bumped a couple of them, it'll obviously give you a little bit inaccurate results, but generally it should be well under a thousandth of an inch accuracy overall. I'll leave you with one little tidbit to keep in the back of your head while you're scanning. This is a tool that is only going to work as good as the person who's actually using it. You can use it wrong and get bad results. If you don't use this with very good care and attention, preparation ahead of time, good scanning technique, make sure you have the right settings and post-processing, you are going to get the results that you put in the effort to get. So learn this scanner, get comfortable with it, and make sure you use it to the best of its ability, and it will perform the way that you expect it to according to the spec sheet. I will be doing another video on volumetric accuracy, and that's going to address large area scans, so large, medium, large objects. Make sure you like and subscribe so that you can get that video when it comes out, and many more videos that deal with scanning and software, all the fun things that we deal with. As always, thank you for watching. I'll see you in the next video.